morning. Today we will talk about model experiments and extrapolation to full scale. Of course, our model experiments will be limited to resistance test only, and sometimes this experiment is called towing experiment, because as we have defined resistance before, it is the resistance of towing a vessel without its propeller working in water. So, sometimes this is called towing experiments or resistance due to towing a model in a tank. Why do we require model experiments? One, of course, we know is to obtain the resistance of the ship in full scale. There is another reason why we do model experiments. As I have explained earlier, we know that the resistance of a vessel cannot be accurately predicted by theoretical means. This also means that we cannot calculate the flow characteristics of water around the ship hull theoretically very accurately. We also know that if the flow characteristics are bad, then resistance may go up substantially. So, it is sometimes necessary to do model experiments to find out how good the flow is around a ship, and if the flow is not as we have desired, it may be necessary to change the model shape at particular locations, or even change the entire forebody or aft body of the model till such time that we can get a better flow, hence less resistance. Flow is important not only from resistance point of view, but also for many other problems such as flow induced vibrations. Imagine a strut projecting out of the ship for some purpose, such as forming a bracket for holding the shaft. If the bracket is not aligned in the direction of flow, there is bound to be eddy shedding or separation near the bracket, in the aft end of the bracket. This separated flow may cause flutter of the shaft bracket or vibration. Similar thing can happen due to flow around a rudder behind a ship, or due to unevenness of flow there can be vibration of the aft body which is not fully supported by buoyancy, that is the overhang of the aft portion. So, these vibrations can lead to harmful effects on the ship, causing vibration in the accommodation or even causing vibrations inside engine room or in particular locations, depending on what type of ship, what type of flow disturbance you have. So, it is many times required to visualize the flow through a model experiment. Now, how do you visualize the flow? We have seen that flow we can understand something about the flow by means of a paint flow test. I have mentioned this before, and sometimes we use wool tufts, small woolen threads attached by means of pins to a model body at various locations, and when the flow past it is seen either through a glass panel mounted on the wall of the towing tank, which is generally not the case, or by video recording the flow, the wool tuft positions on the side of the model, and we can realize if the flow is streamlined or there is existence of separated flow. In that case, it is possible to modify the model shape and do the test again. Sometimes we may do the model test for finding the best forebody or aft body shape, such as we can have 2 or 3 different bulb shapes attached to the same model, the remaining portion remaining same, test them in a towing tank and decide which should be the best shape available to us. So, model experiments are done for a quantitative prediction of, I call it like this, quantitative prediction of EHP. I have told you what is EHP, isn't it? Effective horsepower, or qualitative analysis of form for improvement. Improvement of flow. So, this is the reason why we do model experiments. We will not talk about paint flow test or wool tuff tests anymore, because it is a fairly simple test. We will talk about the quantitative prediction of EHP from a model experiment. So, what are the requirements of a model experiment? That there are two kinds of similarities we will be looking at when we conduct a model experiment. As we have seen, the fluid similarity is the basis of model experiments, which includes geometric similarity between the model and the ship. That means, every linear dimension of the ship of the model should be directly proportional to the linear dimension of the ship. So, what happens is, you come across a model scale, you have to have a scale of the model which is defined as length of ship divided by length of model, and generally this is represented by the Greek letter lambda. So, if I have got a 100-meter ship and I want to test a model of that, I may decide to go for a 2-meter model length, then the scale will be 50. Then every model dimension is reduced by the same ratio. So, what happens to displacement, model displacement? How much should be the displacement? Displacement is reduced from the actual displacement of the ship by lambda cubed times, because displacement is multiplication of 3 length dimensions. Similarly, weighted surface will be reduced by lambda square. All area dimensions will be reduced by lambda square, and all volume dimensions including weight will be reduced by lambda cubed. Okay. What is the tolerance we can give in model manufacture? It is almost impossible to manufacture a model to exact dimensions of the model as we get by dividing by lambda. So, one has to be careful to see that tolerances are within limit. Normally, on breadth we give about a millimeter tolerance, and on length we give a allowance of 2 millimeters. Within that tolerance you should be able to manufacture the model, making sure that tolerance does not mean generation of roughness on the model surface or introduction of additional curvatures than what the main ship should have. ITTC defines, ITTC has given tolerance limits on model scale, and that is ITTC 78 I think, and one can see the ITTC proceedings to know exactly what is the model tolerances recommended by a combined body of all tanks. One point I must mention here, that if you have a larger model, then your tolerances can be better than if you have a smaller model. Let us say, whatever be the material of the model, you can reach only a certain level of accuracy. Say for example, you are generating a surface, that surface can be plus minus 1 millimeter of exact nature. Now, if you have a 2 meter model, then you have that same plus minus 1 millimeter tolerance, and if you have a 5 meter model, you again have plus minus 1 million tolerance. You can understand that the accuracy level for a larger model increases. Right. So, if you want very accurate results, it is preferable to go for a larger model. What is the model made of? Models all over the world are made of wood, wax or FRP. Wooden models were made in earlier years, where they had to be hand finished to get the exact shape of the ship, and it used to take a long time, but with increasing or rather depleted wood resources and the skill for manufacturing models in wood reducing, we have switched over to wax models, which we do in our hydrodynamics laboratory here. Wax models over a wood and bamboo framework. So, it is called a composite model made of wood and wax, or one can make an FRP model. So, that you make a wax plug, a female mold and then the male model. The advantage of making a FRP model is it is thin, but it is strong and it can be preserved. Wooden model can also be preserved, but wax models cannot be preserved. So, wherever you do not require preservation of the model, you can go for a wax model and the model can be destroyed afterwards. Why do you require to preserve the model? It may be necessary for us to study the model characteristics later on, or also do further tests which were not required at the beginning, such as propulsion tests by fitting a propeller, or doing maneuvering tests or sea keeping tests if need arises later on. Nowadays, some tanks are using PVC foam, polyvinyl chloride foam, for manufacturing a model. That also is light, but it does not give the inner surface as much as a FRP model can give for housing other equipments and instruments. The model finish must be smooth. This we have discussed. Model finish must be absolutely smooth, less than 25 microns. Roughness should be there. A micron is 10 to the power minus 6 meters or 10 to the power minus 3 millimeters. The roughness of the model scale should be less than 25 millimeters, which can be considered as 0. So, there is no allowance on model for roughness. I have talked about larger models. Now, if you make a larger model, the model cost is more, and also the facility in which this larger model can be tested will have to be different from the facility in which a smaller model can be tested. You require large quantity of force to be measured, because larger model will give large force. So, you require different sets of instruments and equipment to measure them. So, therefore, larger models are more expensive, and larger model testing is more expensive, because you are going to a bigger tank where more sophisticated equipments are there. So, the scale at this stage one has to determine based on your expense account and the accuracy level you want. It is a compromise between the two. The other aspect you must remember, if you have to go for a propulsion test subsequently, the propeller scale will affect the model scale, because the propeller has to be fitted behind the ship. So, that is the other reason for which you can determine, if you are going for a propulsion test later on, then you must determine the scale of the propeller and the ship model simultaneously, so that later on you do not get into problem. Okay. Now, I mentioned that the tank in which we test the model will be small in case of small models and large in large models. Why did I say that? Can I not test a 5 meter model in a smaller tank? What happens actually is, when I move a larger model in a smaller tank, the waves that emanate, we have seen the waves going from the ship, the divergent waves. They hit the side walls, generating waves, but they normally travel backwards. But what happens is the flow, the distance between the ship side and the tank side reduces on both sides, and also the height from the of the water below the bottom of the ship reduces. As a result, you can imagine if I restrict the flow, then there is a tendency of the flow to go faster. That is, the velocity of water, what it would have been in open sea, would be slightly more if I have the restrictions on the sides and the bottom, which would therefore give a higher resistance. So, what we will be measuring will have slightly higher value than what it would have been if the tank was larger, representing an infinite water domain. We do not want this to happen. That this particular aspect is called blockage. So, our blockage effect should be nil normally. For this, there are some standards set by number of experiments done over maybe 50, 60 or 100 years. That is, length of model should be less than water depth of basin. These are some thumb rules which are accepted world over. Length of model should also be less than half the basin width, and that the one that is most severe is midship area of the model should be less than mid area cross sectional area of the tank. Cross sectional area of the tank is breadth of the tank into depth of water. So, midship area of the ship, that is, if this is my tank, this is my water level, the model midship area, this area should be 1/200th or less of, oh, I have not written the quantity, okay, 1/200 into cross sectional area of the towing tank. That is total cross sectional area of the tank divided by 200, that my midship area should be less than that. Then I can assume there is no blockage effect. If I cannot achieve this, then I should make some blockage correction. The number of literature available in standard textbooks on resistance, which give the references of literature on blockage correction, that can be used. Now, when I say this blockage effect will primarily represent the wave making resistance. It will because the flow will affect the wave making. So, in ships which are moving very slowly, like barges and all, sometimes we may go for slightly larger models without incorporating a blockage penalty. So, this will generally depend on experience of the towing tank personnel. Okay. The other thing, this is regarding geometric similarity, it has so many effects. So, you have to determine the model scale and make the model properly, so that, and the other similarity that must be maintained is called the kinematic similarity or similarity of flow between the model and ship. If flow similarity is not maintained, then what resistance we measure for the model does not represent what happens in case of ship. And if you have a geometrically similar model, the potential flow similarity is automatically obtained, that is the wave making. This we have seen, CR model is equal to CR ship. The main problem comes in frictional resistance. Why? We have seen, let me draw it again. If I plot this as a function of Reynolds number, Cf, what I have seen? I have seen the laminar flow resistance curve goes like this and the turbulent flow goes like this. This is, if you remember, we defined a Blasius laminar flow line and a Prandtl von Karman turbulence line, which was later advanced to the so called ITTC line, which is slightly higher than this, slightly higher than Prandtl von Karman line. But basically whatever formulation you take, there will be a formulation separate for laminar flow. And how do they match? How does the CF catch up with? It should be a continuous curve. You can see this overlap region is a region where both laminar and turbulent flow stays. That is, laminar flow changes to turbulent flow over a region of Reynolds number, and this is normally called the transition flow, like this. Transition flow depends on local conditions. Take for example a ship. We know that the model is much smaller in scale. Therefore, if I take the Reynolds number VL over nu for the model, then it will be much smaller than that of the ship. So, in the model may be in totally laminar region, and it will be more so if the model is smaller. Can you understand that? This is our formulation for Reynolds number. Model is being tested in fresh water, ship runs in sea water, there will be slight difference in viscosity, but they are nearly same. Now, V, since we are maintaining fluid similarity, V of model will be reduced from V of ship by square root of lambda times. Length reduces by lambda times. So, this whole Reynolds number reduces by lambda to the power 1.5. Okay. So, if I have a smaller model, this will reduce further than if I had a larger model. So, larger model will have larger Reynolds number. So, automatically there would be more turbulent flow in a larger model than in a smaller model. Also, we have seen that the fore part of the model, where the flow is just taking place, just starting to develop the boundary layer, the local Reynolds number, that is flow from the beginning till that position, somewhere here in this region, turbulence has not taken place yet, because this is the length here is much smaller than the whole length of the model. Do you understand? So, in the initial part of the ship, there may be existence of laminar flow. Initial part of the model, there may be existence of laminar flow over quite a region. So, if we do not make corrections to this, then again we will be measuring a resistance which is less than what would happen in the case of a ship. We are measuring the total resistance. See what will happen? We will measure little less resistance because the flow is turbulent, and then because the flow is laminar, we will measure less resistance, then we will use the turbulent friction line to reduce the frictional resistance. So, CR that we will get will be less than what the ship would actually have. Am I clear? We have said CT equal to CR plus CF. Now, if CT is less because of presence of laminar flow, this CF we are calculating on the basis of ITTC line, which is turbulent flow. So, this CR will be less. So, when we extrapolate to ship, we use a less CR than actually what the ship should have. So, we will be under predicting resistance, which is not at all desirable. You can over predict a little bit, but you cannot under predict. So, for this reason, it is essential for us to ensure that the flow is made turbulent. So, we have to use turbulence stimulators. Turbulence has to be stimulated. We have to stimulate turbulence in the fore part of the ship. And how do you do it? We will have to introduce artificial roughness at the front end of the ship, so that the flow becomes turbulent because of existence of rough surface. As if we are introducing forcible turbulence on the ship forebody. And what we use is called tripwire. This is the normal turbulence stimulator used in ships. That is, I got a ship model here. I can put a wire right on the front of the ship, or if this is the FP, about 5% length aft of FP, LWL, length on water line. Normally model test we use length on water line. So, I can put a tripwire here, that is, if I draw the section here, the section of the ship may be like this. I put a small tripwire all along the model with small anchors holding it by pins. If I have got a wax model, I can put pins and hold the tripwire, small pins which will insert itself into the model. Now, suppose I have put a tripwire here. What is the guarantee that the flow here is turbulent? The initial flow here will be turbulent, but because of pressure difference, we have seen there is a relationship between pressure and velocity. Because of such pressure differences, the velocity may further drop. If the pressure difference is high, pressure is high, then velocity may drop further. If velocity drops, turbulence again may fall, because Reynolds number will local absolutely regional Reynolds number will come down again. So, the turbulence that you created may be suppressed again and laminar flow may take over. So, it is common practice to use not only one, but maybe 2 tripwires at another maybe 10% distance or 7.5% after, it depends on the type of model, type of fullness, etc. So, this is how the turbulence is stimulated. Sometimes instead of tripwire we may use studs. Studs are, again if I draw the section here, studs are small little projections here at small intervals. These are studs, or we may use sand strips, sandpaper strips. Small sandpaper strips may be fixed at around the ship's girth at the forward end at 5% aft of AP and 10%, sorry 5% aft of AP and 10% aft of AP. So, this is how turbulence stimulation is used. Now, one has to be very careful, we are adding extra appendages to the model. As long as it is limited to only turbulence stimulation, it is fine. It may so happen that it actually adds resistance, is not it? That can also happen. If I have appendages, it may also add resistance. So, we have to make a compromise how much turbulence stimulation has to be given, so that just about turbulence is simulated, but it does not add its own resistance to ship resistance. So, this has to be done carefully. Now, how do you do this? How do we know the existence of laminar flow in a model? It can be easily got obtained from the model experiment itself. If I have plotted Rn here and Ct here, I know my Cf line is like this and 1 plus k Cf line is this. And mind you, laminar flow will mostly occur at low speed, because the speed is low, Reynolds number is very low. If we actually go for high speed, laminar flow may be suppressed to a large extent, depends on model scale. Now, here we have seen that the resistance curve should have been like this, that is at low speeds it should follow this line when there is no CR, and then it goes like this. It may so happen you will find that the resistance curve is actually going like this, or even coming down to this line, even going below the CF at low speeds. Then you know something is wrong here, and the reason for this will be laminar flow. Now, all these things I am telling is very simple to hear on the drawing on a piece of paper. Actually, when you do experiments, the resistance at low speeds is very low. So, there is bound to be, if the measuring equipment has a small error, a constant error, then that reflects here maximum, because the quantity we are measuring is small. So, the error part of the model experiments shows mostly at low speed region, whether it is Rn, Fn or speed, whatever we plot the graph with. If there is an error, it shows mostly at low speed, and therefore, I mentioned before also the estimation of k itself and the nature of the curve here is always a little suspect, and this suspicion reduces if you go for bigger models in a bigger tank. Okay. Right. Now, we have seen the model, we know how the flow similarity has to be maintained. What about the carries? The carries, how does the model get towed in a tank? You have to tow the model. We have said it is a towing experiment. Initially, we mentioned that a resistance experiment is called a towing experiment. So, if I have a ship model here, if this is the water level, if I moved it at a constant speed, its resistance will act opposite horizontally, and the entire total resistance will have a centroid somewhere in the middle, where the resistance will act this way. Am I right? Yes. The resultant you can easily calculate if you take moments of the individual resistance components and calculate, then you should get this thing, if you know at each section what is the resistance. If you know, we do not know, but roughly it will be somewhere in the middle of the length of the ship and somewhere in the middle of the draft, or maybe slightly lower, because the bottom portion will come. I should be able to pull the model at this point, providing a force equal to the resistance. My tow rope pull should be, if I ask this tow rope pull, I give a pull to the model, that should be equal to RT, isn't it, and applied at the same point, that is resultant point where the resistance works. Now, as I have mentioned, we do not know where the resistance works. We only know that it can be somewhere in the middle of the ship, maybe midship, and slightly less than half the draft, above the keel line, right. This is all we know. Suppose they are not on the same point, what will happen? Suppose this P I have applied here, what will happen? It will give a small trimming moment. Now, hopefully, this trim will not be large to affect the model resistance. You remember, we assumed that the model will not trim or sink. One of the assumptions we made for any calculation on resistance, that the between model and ship, the trim should be similar, geometrical similarity has to be maintained. Now, by putting the tow rope point somewhere above the where the resistance worked, I will be introducing a small trim. Now, since I do not know where the resistance is, I cannot help it, it will come, small error will be there. But mostly in all the model experiments that have been carried out for merchant ships within less than 0.3 Froude number, putting the tow rope point at half the draft or slightly less than half the draft has not shown any change in trim and sinkage. If you think of trim, actually we know there is pressure acting, normal pressure acting on the ship surface. We have found out the axial component of that, and we have said that that is equal to resistance. What about the vertical component? We have said the vertical component gives buoyancy, right. Now, I am moving the ship, that was in static condition, when there was no axial component, only vertical component. Now, moving the ship, the pressure distribution changes everywhere. We have said the horizontal component is equal to resistance. What about the vertical component? that will not remain same because pressures are different now. So, it may so happen that if there are large changes in vertical component of the force in the fore part and aft part, the vessel may actually trim. Okay. But if I am maintaining kinematic similarity of flow, then whatever trim the ship will face, my model will face the same trim, geometrically similar trim. Am I making myself clear? So, when I am talking of this trim, this is in addition to that trim. All we have to take care is this does not cause any trim. So, as I said, to about 0.3 Froude number, there is no visible trim of the vessel and there is no visible trim in the model. So, this method is more or less okay, but one has to use one's own perception of the resistance force, how it is acting for other cases, particularly high speed vessels, when we are going beyond 0.3 and the pressure forces do cause a trim, how the toe hook position should be for applying the toe pull. Do I make myself clear? So, this point is very important and we have to keep it in mind. I am not saying that it has to be done accurately, it can't be because we do not know. For example, if I am talking of planing craft towing resistance, the vessel actually comes up, it lifts itself. So, the bottom is more or less near the water surface. So, actually in that position my toe hook should be near the attached to the bottom of the ship, but I can't attach it to the bottom. It has to be, there must be some distance between the bottom and actually the attachment point. So, I do introduce small amount of error, but my effort should be that this error should not affect my resistance which I am going to extrapolate. Okay.
But how do we come to nearby this point? Means almost accurate, how we come to this?
Oh, that's by experience. For example, for 0.3 up to 0.3 Froude number, half the draft is a good enough measure, or slightly less than half the 1/3 to half the draft from bottom. That is the range in which we can fix, because you see any fixing device you make, it has its own thickness, own sitting arrangement. You do not really have that much of accuracy that I will just take it to half the draft. So, it will be between 1/3 draft to half draft from the bottom, that is the rule. In a planing vessel, we try to bring down the toe hook point as much as low as possible, that is all. You can't do more than that. Sometimes to ensure that toe hook is not introducing in error, we do this many times. We attach the toe hook at 2 or 3 different positions and repeat the test to see that we are getting same results. Sometimes one has to do it. Okay. Now, one thing we have known that whatever arrangement you make, this toe hook, how do I apply the pull? It must be applied from top somewhere, isn't it? So, what we have is what is called a resistance dynamometer. Okay. And this resistance dynamometer is a device which is held by a carriage on top of the model, the carriage being held separately on rails mounted on the towing tank. So, the carriage and model have no connection except through the dynamometer. A dynamometer is held by the carriage and it has a pillar which moves inside the dynamometer. This pillar is fixed on the model. So, model takes the pillar, but not the dynamometer. The pillar is free to go up and down in this thing. Now, this arrangement is such that, as we have said here, just in this diagram what we said, that the model can go up and down. This pillar must allow free sinkage of the model, that is free flotation, and also must allow trim and heave motion. The towing arrangement must provide. Sometimes it is through this one point attachment, sometimes the dynamometer is too large and you cannot have this one point attachment, then you can have guides on the model through which the carriage on the tow dynamometer and the model are kept in single axis. So, the model is free to heave and trim.
So force also has to be exactly horizontal.
Yes, that is why the dynamometer is attached, and the attachment is such that the force is horizontal and axial. There is no transverse force. Therefore, there is no roll, sway or yaw. The model is constrained against roll, sway and yaw. It can only heave and trim, and you must have measuring devices to measure the resistance, the force, the heaving and the trimming. The other thing that must be measured is the speed. So, the carriage is the one that provides the speed, constant speed.
So, but due to the friction of the rails and all, it won't vary.
Carriage speed, carriage is attached to the model by the dynamometer. So, as long as the carriage, what force the carriage takes, we are not bothered. The dynamometer, the pillar, what force is exerts on the model, that we are bothered. That we measure through a strain gauge type of measurement between the pillar and the housing that is held. So, if the housing is exerting a force on the pillar to pull it, that is measured through a strain gauge type of instrument. And similarly, we can measure the sinkage and trim. So, this is how the model experiment is conducted. How do you prepare the model for experiment? Preparing the model, we have manufactured the model, we know the light weight of the model, we know what should be the displacement. What we know of the model, with this we know the draft forward of the model and draft aft of the model. Known quantities are this, right. So, this displacement of model will be equal to model weight, light weight, this is light weight, light model weight plus weight of dynamometer supported by model. You see this pillar that will sit on the model. So, that weight will come on the model, that will not be held by the carriage, plus to get the proper displacement we have to add ballast weight. Okay. So, you have to calculate how much ballast weight will go, and then the model has to be weighed, and you can get the model displacement similarity. What is draft aft and draft forward? That is ship draft divided by lambda, geometric similarity, and similarly draft aft is, that is trim angle is same, angle will be same. So, this has to be, model has to be prepared. When attached to the carriage, this is achieved. Once this is achieved, you run the model at different speeds and get the resistance. Can I quickly go over extrapolation procedure? I think I will do it very quickly because we do not have much time. We are measuring VM, RTM, sinkage and trim. For normal conventional merchant ships, we will ignore this. This is important for other types of vessels, but not for conventional displacement type merchant ships moving below 0.3 Froude number. What else do we know? We know model displacement, model weighted surface, length on waterline of the model, right, and we will see what else is required. All this is known. We have also measured, we also have to measure temperature of water. Because the density and kinematic coefficient, these two items that are very important for our calculation are temperature dependent. So, we have to measure the temperature to get these values. Now, let us see how are things extrapolated. Speed of model Vm gives Vs equal to Vm into root lambda, right, fluid similarity, fluid number Vm by root G Lm equal to fluid number ship, fluid number is same, density of water, and this is fresh water. For model, rho model is fresh water at temperature measured, okay, and ship sea water, and for all calculations we take 15 degrees centigrade as standard temperature, 15 degrees centigrade, and this sea water density at 15 degrees centigrade is 1025.9 kilograms per meter cube. At same temperature, rho m is 999 kilograms per meter cube. So, you see there is an increase in density. Kinematic coefficient, similarly for model it will be fresh water at measured temperature, and ship will be equal to 1.18831 into 10 to the power minus 6 meter square per second. This unit we have seen yesterday. So, this is the standard kinematic coefficient of viscosity at 15 degrees. So, using this we can calculate Reynolds number, RTM and RTS can be calculated, right. I am giving you steps. Now, CFM is equal to 0.075 log 10 RNM minus 2 whole square. This is ITTC line, right, and we can calculate CFS. Similarly, we got all the values. Calculate CT for model, CTM for model, and form factor K. There is nothing to do with the ship. From the resistance curve you can calculate using the value at fluid number equal to 0.1 as we have discussed before, or drawing the full curve and seeing where it is parallel to the CF. We have seen some methods of calculating form factor. Then CRM is equal to CTM minus 1 plus K CFM, right. CRS is equal to CRM. So, CTS at this stage is equal to, I'll just put a 1 here, CRM plus 1 plus K, or CRS, we have already said this is equal to CRM, CFS. This we have calculated. Okay. Now, we have said that there will be a correlation allowance, that is CA. I told you yesterday that ITTC has given a length dependent CA value, and that formulation is like this: 105 into Ks divided by length LWL to the power 1/3 minus 0.64 into 10 to the power minus 3, where Ks is the roughness of the surface. Normally for new ships, Ks is taken as between 125 to 150 microns or 10 to the power minus 6 meters, all in metric units. Okay. So, this for a 400 foot ship it would come to about 0.4. Then we have the appendage resistance. You have to calculate the appendage resistance and convert it to a coefficient, so that you can add it to CT. and similarly you have to have the wind resistance coefficient. Again calculate the total wind resistance, divide by the total weighted surface, how the CT is calculated, half rho S V square. That S may be changed to S plus appendage weighted surface. Then you can calculate resistance for the total ship including that of appendage weighted surface. Then you get CTS is equal to CTS 1 plus CA plus CAPP plus CAA. All this will give you the actual ship resistance either at 0 before or at before 3. The CAA will determine that depending on what sort of trial condition you want to do. Once you get CTS, you can calculate RT as half rho S plus SAPP rho S Bs square for various speeds, and EHP effective horsepower we have seen will be equal to total ship resistance into into CTS. Okay, and if this is in kilonewtons, this will be in kilowatts. This is in meters per second, this will be in kilowatts. Now you have to be careful because the whole calculation we have given is in newtons. So somewhere along the line you have to convert it to kilonewtons, maybe dividing by 1000. Okay. So this is the way you have to extrapolate from model scale to full scale. We will stop here today. Thank you. Good morning, gentlemen. Today we will talk about how the resistance of a ship gets affected if it moves in shallow water as compared to its movement in deep water. Practical experience of course has shown us that when a vessel goes from deep water to shallow water, typically from a sea to a river, speed drops tremendously. We will see if it is possible for us to determine a speed power relationship or speed resistance relationship in shallow water, taking the values of deep water as known. What happens in shallow water? Imagine a vessel moving in a limited water depth. As the vessel moves forward, the water flows past the ship as we have seen, and because of restricted availability of water depth, the water will speed up at the bottom. The velocity will increase. If the velocity increases, what will happen to pressure? Pressure will drop. We have seen previously that as in the midship region, that is middle of the ship, the pressure is low anyway. So this pressure falls further, and as it falls further, the immediate effect is with the same immersion of the ship, the upward force reduces. Therefore, the vessel will experience a sinkage, because ultimately for the vessel to remain afloat, buoyancy has to equate weight, right. So, if the pressure drops in a large portion of ship's length, buoyancy reduces at the same water level. Therefore, the vessel must experience a sinkage so that the buoyancy and weight equalize and the vessel. Scrape the paint, short blast the surface. Short blasting is done primarily to smoothen the surface, and then paint it again. It should become as good as new, but it has been found by measurement that generally even after a 5-year survey, there is a small increase in roughness. the ship never comes back to the new condition in spite of replacement of plates which have reduced to a large extent in thickness. In between these 5 years, what happens? The plate roughens, of course, and there is large amount of fouling. Fouling may be removed once in a while, but generally fouling will grow. Fouling is a biophenomenon depending on the environment in which the ship is operating, that is whether it is tropical climate or temperate climate, and whether it is moving or not moving. It is fairly well known, if the ship spends a large time in ports, particularly tropical ports, fouling is very heavy. So, when it goes out after being in a port, the speed drops. Now, the roughness, resistance increase due to roughness can be calculated using this formulation if we know what is the roughness Ks of the ship at any time. But it is very difficult to estimate the resistance due to fouling because of the uncertainty in growth of fouling, as I have said. If we can estimate from the measured speed, if we can estimate the resistance increase, we know at what point of time we require to maintain the hull. Maybe a scraping of the hull, removal of foulings even in afloat condition may be desirable. But more important is the trial condition, which I have always said is a very critical for the shipbuilder and ship owner. You have taken the ship to the dry dock, cleaned the ship, painted the ship again, and you are ready to go out to trial. For whatever reason, it may be as simple as the surveyor not being available, or the lifeboat not being available, hence the ship cannot go out to sea, or maybe some major production problem. It could also be that there is a storm brewing and you have to wait for 15 days after you have undocked the ship to go to sea trial. This 15 days is critical, because what is happening? The ship is standing in water in a port environment for 15 days. So, the fouling that will come up in this case will definitely show you a drop in speed. So, you have to be careful when you go out for trials in what condition your ship is, and if you cannot bring back the ship to its original new condition, you must be able to apply suitable corrections to get the proper trial speed. Okay? I think we will stop here. Thank you.